Section 10.3 is going to give us another test for convergence. It's called the integral test. From here on out, we're just working with infinite series. Series, remember, where we're adding terms together. A corollary of Theorem 6 says that a series n equals 1 to infinity of a sub n of non-negative terms converges if and only if its partial sums are bounded from above. What that means is that we've got some conditions that we need to check if we're going to use the integral test. When we use the integral test, we're going to rewrite the terms of the series as a function of x. That function has to be continuous, positive, and decreasing in order for us to use the integral test. A harmonic series is a divergent series because of the sequence of partial sums is unbounded. So a harmonic series is just the sum n equals 1 to infinity of 1 over n. And we can prove, and we will prove, that this is going to diverge. Let's go ahead and prove it now. If I rewrite the terms of this series as an integral, I would be looking at the integral from 1 to infinity of 1 over x dx. And I could rewrite that integral as a bounded integral from 1 to b. It's the limit as b approaches infinity of 1 to b of dx over x. And when I integrate dx over x, I'm going to get natural log of x. So this is going to be equal to the limit as b approaches infinity of the natural log of x evaluated from 1 to b. So when we plug in our upper bounds, we're going to get the natural log of b, and when we plug in the lower bound, we get the natural log of 1. The natural log of 1 is 0, but the natural log function goes off to infinity. Remember, the graph of a natural log function looks like this. So as b goes to infinity, that natural log continues to get bigger and bigger. And remember, in the last section, we said that divergence dominates. So this integral is going to diverge, and therefore, by the integral test, this series is going to diverge. And I haven't formally given you the integral test, but I'm about to. In example 2, we're asked, does the following series converge? Well, what we're going to do is we look at the graph of 1 over n squared, and this graph we see is continuous, positive, and decreasing. So that means that I can look at the integral from 1 to infinity of 1 over x squared dx. And that's going to be equal to the limit as b approaches infinity of the integral from 1 to b of x to the negative 2 dx. And when I integrate this, I'm going to get the limit as b approaches infinity of negative 1 over x bounded from 1 to b. And as b approaches infinity, this term is going to 0, so I get 0 plus 1, and that's equal to 1. And because the integral converges, that means that the series is going to converge. This looks an awful lot like the harmonic series up here, except that we had a power on the n in the denominator. The harmonic series diverges, whereas this series is going to converge. And we proved that, or we showed that, using the integral test. Theorem 9 is the integral test. Let a sub n be a sequence of positive terms. Suppose that a sub n can be written as a function of n, where f is a continuous positive decreasing function of x for all x is greater than some number. Then the series and the integral are both going to do the same thing. So when you use the integral test, you have to check 3 things. When you rewrite your series as a function of x, you've got to check to make sure that it's continuous, positive, and decreasing. And if those 3 things happen, then both the series and the integral will do the same thing. That's why I said in the first example that we looked at, because the integral diverged for the harmonic series, the series diverged. And for example 2, we said because this integral converged, the series converges. Now what this integral is equal to is not the same thing as the sum of the series. We'll talk about how to find or approximate the sum using the remainder theorem towards the end of this section. In this example, we're asked to use the integral test to determine if the series shown below converges or diverges, and be sure to check the conditions. When you check the conditions, what you want to do is you want to graph that function. And when you graph this, be sure to put the denominator in parentheses. I scaled my axis so that this would be 1, and this series starts at 1, so what I'm looking at is what is the function doing after that point at 1. Well, when I graphed this argument of this series, I see that my function is continuous, it is positive, meaning it's above the x-axis, and it is decreasing, for x is greater than 1, greater than or equal to 1. So these three conditions are satisfied. So to check the convergence of the series, what I'm going to do is I'm going to look at the limit as b approaches infinity of the integral from 1 to b of 3 divided by x squared plus 4 dx. Now, how can I integrate this? We just had a test over techniques of integration. What technique could I use in order to evaluate this limit? Use trig sub. We're going to use trig substitution in order to evaluate this limit, which means that I need to set up a triangle. So here's my right triangle. There's my angle theta. What will the hypotenuse be? Remember, that's always what you want to ask yourself. What is the hypotenuse going to be? Square root of x squared plus 4. That means that the opposite side is going to be x and the adjacent side is going to be 2. X over 2 is going to be equal to opposite over adjacent, which is tangent. So that means that tan theta, or let me write it like this. That means that x over 2 is equal to tangent theta. So x would be equal to 2 times tangent theta. Dx would be equal to what? 2 secant squared theta d theta. Do not forget your differentials. And then the other thing I'm going to need is the radical, but there's no radical here. How do I account for that? I could rewrite that as the square root of x squared plus 4 squared. So that would be that over 2 is hypotenuse over adjacent. Hypotenuse over adjacent is equal to secant theta. So the radical by itself would be equal to 2 secant theta. But I don't have the radical, so if I square both sides, I'm going to get x squared plus 4 is equal to 2 squared times secant squared theta. When we change the variable of integration, what is the other thing that we have to do? Change the bounds. So let's start with the lower bound. I'm going to replace x with the lower bound here, and I get 1 over 2 is equal to tan theta. That means that theta is going to be equal to tan inverse 1/2. And to get your new upper bound, we're going to look at the limit as b approaches infinity of infinity over 2. And so for our upper bound, we're going to get infinity equals tan theta. And for what angle is tangent going to be equal to infinity? It's where cosine is equal to 0. That's going to be pi over 2. So this is our lower bound, our new lower bound, and this is our new upper bound. That means that I can rewrite this integral. It's the integral from tan inverse 1/2 to pi over 2 of 3, and in place of the dx, I'm going to plug in 2 secant squared theta d theta over, and we said that x squared plus 4 is going to be equal to 4 secant squared theta. So the 2 will go into the 4 2 times, and that's going to give us 3/2 times the integral from tan inverse 1/2 to pi over 2 of the secant squares are also going to cancel out, so this is just going to be d theta. And that's going to be 3/2 times theta evaluated from tan inverse 1/2 to pi over 2. That's going to be 3/2 times, plug in your upper bound, and you get pi over 2 minus tan inverse 1/2. All right, so since this is a positive finite number, I don't need to get a decimal approximation. The integral, we say, converges because I got a final answer. Well, if the integral converges by the integral test, that means that this series is also going to converge. So our conclusion here would be that our series converges by the integral test. In order to reach this conclusion, I need to see the work. Well, I need to see you write down somewhere that you checked that this function was continuous, positive, and decreasing. You don't have to show me your calculator or write down what the graph looks like, but you do need to mention that you checked to see that your function was continuous, positive, and decreasing. Then I need to see the work where you evaluated the limit and got a final answer for the limit. This was the answer for the limit, and then your conclusion is that the series converged by the integral test. Now, if we look back at these first two examples that we did, I want you to pay attention to the power on n in the denominator. When the power here was 1, the series diverged, but when the power was 2, the series converged. That's going to lead us, or that observation leads us to our next test, which is called the p-series. If you have an infinite series written in the form 1 over n raised to a power of p, then this series is going to converge if that power is bigger than 1, even slightly bigger than 1, like 1.01. And it's going to diverge if p is less than or equal to 1. We proved something similar to this in section 8.8 video when we had to do those proofs or find the values of p where the series converged or diverged. And I told y'all that this was coming up, and here it is. You can find the P series on your summary for tests for series. Right here, it's the 1, 2, 3, fourth one down. And it basically says the series is going to converge if the power is bigger than 1, and it diverges if the power is in between 0 and 1. We don't worry about negative powers because we would make those positive. In example 2, we're asked, does this series converge or diverge? We can rewrite this series in a form that makes it easier to identify what type of series it is and whether or not it's going to converge or diverge. What does this series look like? It looks like a geometric series. The geometric series looks like this, and it converges if the absolute value of r is less than 1. What would a be for this geometric series? 1. And what would r be? 1/9. 1/9 is less than 1, so therefore this would be a convergent geometric series. So we would say, if this was a multiple choice question on a test, we would say the series converges because it's a geometric series where the absolute value of r is less than 1. It's easier to identify that if we rewrite the series. So anytime you have 1 over something raised to a power of n, you can rewrite that as the fraction raised to the power of n. In example 3, this one would also be easier if we rewrote it. What could I write this series as? We can distribute the exponent, or when I undo the distributing of the exponent, I would get 2/3 raised to a power of n. Is this series going to converge or diverge, and why? It's a geometric series where r is equal to 2/3, so it's a convergent geometric series. What about this series? This one's not a geometric series because I've got this natural log and I don't have powers. It's not a p series because that n's not being raised to a power in the denominator. So our options here are either the integral test or the nth term test. So the easiest test to use when you have a choice is the nth term test for divergence, because it's really nice if the series diverges. So let's check out the nth term test for divergence first. That means that I'm going to look at the limit as n approaches infinity of the natural log of n plus 1 divided by n plus 1. As n goes to infinity, the natural log is going to go to infinity, and the denominator is also going to go to infinity. That means that this is in an indeterminate form, so I can use L'Hopital's rule to evaluate this. So I'm going to look at the limit as n approaches infinity of the derivative of the natural log of n plus 1 is going to be 1 over n divided by, and the derivative of n plus 1 is 1. And as n approaches infinity, this is going to 0. Does that tell us anything? The limit of the nth term is equal to 0. When we look at our nth term test, if the limit is not equal to 0, we know the series diverges. What happens when the limit is equal to 0? It's inconclusive. That means we got to try something else. The something else that we're going to try is the integral test. So because the nth term test is inconclusive, we're going to try the integral test, but there's 3 things that we have to check before we can use the integral test. So I'm going to graph my function, and my window went from 1 to 10 here. And one of the things we have to check is that this function is continuous, positive, and decreasing. Clearly the function is continuous, and it's positive because it's above the x-axis, and it's not decreasing before 1. This integral starts at 3, and here's 1, 2, 3. So once I get past 3, my function is decreasing for n greater than or equal to 3. So all 3 conditions that we need to check are satisfied. Now I'm able to set up the integral from 3 to infinity of the natural log of x plus 1 divided by x plus 1 dx. How am I going to evaluate this integral? We're going to let u be equal to the natural log of x plus 1. What is du going to be equal to then? What's the derivative of the natural log of x plus 1? Well, the derivative of a natural log is the derivative of the argument over the argument. And notice I've got 1 over x plus 1 dx right here. And if I'm going to change my variable, I then need to change my bounds. My old lower bound was 3, so my new lower bound is going to be the natural log of 3 plus 1, which is the natural log of 4. My old upper bound was infinity, and when I plug in an infinity in place of x, the natural log of infinity is still going to be infinity. So that means I can rewrite this integral as the limit as b approaches infinity of the integral from the natural log 4 to b of This is just going to be u du. And when we integrate this, we're going to add 1 to the exponent, divide by the new exponent, and that gives me 1/2 u squared. I'll just put u squared over 2 from the natural log 4 to b. Applying the fundamental theorem of calculus, this is going to give us b squared over 2 minus the natural log of 4 squared over 2. And as b goes to infinity, this term is going to infinity, and infinity minus a number is still infinity. So what does that tell us about this series? It diverges by the integral test. So we would select this one right here. So when you use the integral test, make sure you check to see that your function is going to be continuous, positive, and decreasing. Evaluate the integral, and if that integral converges, then the series converges. If the integral diverges, then the series diverges. And the last thing we're going to talk about, bounds for the remainder in the integral test. When we use the integral test, the answer that we get for our integral is not the value of the sum. We want to be able to approximate the value of the sum of a series. I'm going to use a picture to explain this concept. We're going to say that the sum of some series, let's use this graph and let's let the area under the curve represent the sum of the areas. We would say then that the sum is equal to some nth partial sum plus some remainder for that nth partial sum. The total area under the curve here would represent the sum of this series. Suppose a sub k is a sequence of positive terms with a sub k equals f of k, where f is a continuous positive decreasing function of x. That means that we can use the integral test to test for convergence. And that the sum of a sub n converges to s. So that's what that series converges to. Then the remainder, r sub n, is going to be equal to the sum, which we don't know what it is, but we know that it exists, minus some nth partial sum. It's going to satisfy these inequalities. So the total area under this curve right here would represent the sum. We don't know what that is though, because it's not exactly the same as the area under the curve. But we're going to take an arbitrary point here. Let's call this S sub n. This area right here we would use to represent, this would be A sub n. This area right here would represent the nth partial sum. What's left over out here is going to be the remainder for the nth partial sum. It's what's left over. So can you see how I said the sum is going to be equal to the nth partial sum plus the remainder for the nth partial sum? Well, if I subtract S sub n from both sides of this equation, I end up with this equation right here. R sub n is equal to the sum minus the nth partial sum. The remainder can then be trapped or bounded between, it's going to be bounded above by the integral from n to infinity of our function and be bounded below by the integral from n plus 1 to infinity. There's another picture in your book that does a good job of showing this, but I don't have it. If we add the partial sum S sub n to each side of the inequality here, so what we're going to do is we're going to add the nth partial sum, then I get R sub n plus the nth partial sum. Well, R sub n plus the nth partial sum is equal to the sum. So what I can do is I can get a bound, a lower bound on the sum of that series and an upper bound by adding the nth partial sum to the integral from n to infinity. If I just add the nth partial sum here, here, and here, I end up with this down here, the nth partial sum plus the integral from n plus 1 to infinity and the nth partial sum plus the integral from n to infinity. This one, the lower bound starts at n plus 1 because n plus 1 would be further out, which means that I've got a lower bound on my remainder. And this value here is the nth partial sum. We're going to use this to be able to estimate the sum of an infinite series using the integral test. So let's say you're working on a problem in the real world and you need that area to be within a certain tolerance. That would be what we consider our area. This example explains how we do that. It says estimate the value of the infinite series from 1 to infinity of 7 over n cubed to within 0.098 of its exact value. What we're going to do that is we're going to set up an inequality here. What this means is that we want our series sum minus some nth partial sum to be less than 0.098. Whatever the true value of the sum is, minus some nth partial sum, that has to be within 0.098. My goal is to approximate the sum by finding what this nth partial sum is that'll give me this tolerance here. In order to do that, I'm going to use this side of this inequality. So that means that I can set up the integral from n to infinity of my argument 7 divided by n cubed, and I don't want to use n's here, I want to use x's dx. That integral has got to be less than 0.098. That means that I can rewrite this as the limit as b goes to infinity of the integral from n to b of 7x to the negative 3 dx, and that's going to be equal to the limit as b goes to infinity of negative 7/2 x to the negative 2, which is negative 7 over 2x squared from n to b. So whatever this is equal to has got to be less than 0.098. So I'm going to evaluate the bounds here, and that's going to give me the limit as b approaches infinity of negative 7 over 2b squared plus 7 over 2n squared. And as b goes to infinity, this term is going to go to 0. And that means that I'm going to get 7 over 2n squared, and that has to be less than our tolerance of 0.098. What I'm doing is I'm going to solve for the value of n to see what that nth partial sum needs to be. So this gives me an inequality that I can then solve for n. I'm going to put this over 1 and then cross multiply. So that's going to give me 7 is less than 2 times 0.98 is 0.196 n squared. Divide both sides by 0.196 and that gives me 7 over 0.196 is less than n squared, but if I want the square off of the n, I'm going to have to take the square root of this number. So this ends up being the square root of 7 divided by 0.196. So that means that in order for this sum to be within this tolerance, n has got to be greater than, because I'm switching the inequality, we'll call it 5.98. Since n has to be bigger than 5.98, that means I'm going to use n equals 6. And so to be within this tolerance, what I'm going to do is I'm going to find, this was all scratch work, I'm going to find the sixth partial sum, which will be the sum n equals 1 to 6 of 7 divided by n cubed. So I just need to add the first 6 terms of this together. Fortunately, our calculators will handle finite sums. Hold on a second. If you hit math, go down to summation, it's number 0 underneath math. I'm going to use x for my variable, and x is equal to 1 to 6 of 7 divided by x cubed. And we see that the sum is approximately equal to 8.332. And this would be within a tolerance of 0.098. That's how you would approximate the sum of an infinite series if you know some tolerance. And this wraps up section 10.3.